machines, you will have the host kernel, then hypervisor, guest kernel, then some middleware, library, and application. But in case of containers, we have a host kernel, and then there is some container engine, which can be like a Docker, which actually provided this isolation using namespaces and control group. And then on top of this, your application runs. Now we can run our microservice inside the container, and we can run container on a single host, but we don't want to do that. Just consider your host node goes down, even your application goes down. So in a production environment, we need certain features from the application, like high availability, failover, service discovery, rolling updates, etc. And that's where the container orchestrators come into picture. So typically what happens is that we deploy the container in the cluster environment, and then there is a container orchestrator which makes sure that your container is highly available and rolling updates and all of the features are quite easy. One such orchestrator is Kubernetes. Kubernetes was developed by Google. Another container orchestrators are like Docker Swarm, Mesos, etc. Now, I'll explain the architecture of a container orchestrator using Kubernetes, but most of the components are similar across different container orchestrators. There are minor differences. So let's take one example to explain this diagram. So consider I want to run a microservice inside a container, and I want that there should be 3 replicas of my microservices always running. And I want that my microservice should run on the nodes where SSD is installed. So this is something I call it as a desired state for my application. And this desired state can be put in some kind of YAML file or some kind of JSON object. Then there is some interface like kubelet, which takes this desired state and sends this desired state to a master node. On the master node, there is an API server which takes this desired state and puts it into some distributed database. So in case of a Kubernetes, that distributed database is etcd. Then there is one component as a scheduler which keeps watching for such requests. So what happens is the scheduler will pick this request and it will spawn 3 instances of your application or container on 3 different nodes where SSD is installed. Right? Now consider one of the node goes down. Then there is one component as a controller manager. So it checks whether any node has gone down, and it will restart your application on another node so that the replica count is maintained and we are achieving the desired state. Now containers are ephemeral. Means you start a container, you run some workload, and once container finishes, everything inside the container is gone. But storage is not. Storage is having a state associated with it. Now, before digging into the container storage, let's at a high level talk about what are the different kinds of storages we are having. So typically we have 3 kinds of storage. The first one is a block storage, where we split the big volume into some fixed size chunks. It is highly performant and well suited for transactional kind of workloads like DBA and all. Then we have a file storage. It is simpler to use because your data is organized in files and folders. Then we have an object storage, where you are having a big data which is not getting modified so frequently. For example, your video files, music files, etc. Now, when containers were started, at that time it was used to run the stateless application. But later it was realized that we want to run the stateful application inside the containers, like databases. Now, in case we want to run the stateful application inside the container, we need some persistent storage attached with the container. And that's where the container storage comes. So let's try to understand some ways by which we can attach a storage to a container. So the first one is a local host storage. So consider that there is a node and I'm having some path on the node. Let's say /ABC. So we know that the container runs in its own isolated environment, in its own namespace, where it is having a separate mount namespace. So what happens is that whatever the path is there on the host node, that gets bind mounted inside the container. So that is how the connection happens between your host path and the way the container can access it. It is through the bind mount. So this is how the local host storage can be used. But there is one problem here. Consider that this node goes down and the orchestrator starts your container on the different node. It could be possible on that node this path is not present, and then your workloads will start failing. So the other kind of storage is the storage appliance. In this case, the storage is sitting outside the host. And the interface to the storage can be like NAS, SAN. And since multiple host nodes can access this storage, even if a container moves from one host node to another, they can access the storage and the workloads can work. The third kind of storage is a distributed file system, like OpenAFS. And I think it is one of the simplest way to provide a storage to the container because of the advantages of the distributed file system, like global namespace, transparency, etc. So let me take one example. So there is a node where we are having some AFS path, let's say /AFS cell name, and let's say ABC. And then we start a container on that node. So what happens is that this path gets bind mounted inside the container, and then container can start doing some IOs. And later, consider that node goes down, and if that container moves to a different node, it will still find that /AFS path, and that's how the workloads can work seamlessly. So now, since we have understood some different kind of storages which we can use inside the containers, let's take one example with one of the container orchestrator like Kubernetes. Now, before starting that, we need to understand some basic terminologies in the Kubernetes, like the persistent volumes and persistent volume query. So let's take one example here. So there is an IT administrator, and IT administrator has provisioned 4 volumes like PV1, PV2, PV3, and PV4. There are different sizes using different storage patterns. Like in this case, it is iSCSI and NFS. Once the storage admin creates these storages, somehow the admin has to tell the container orchestrator, that is Kubernetes, that these storages are available. And the way that is done is using persistent volume object. So what the administrator will do is, it will create 4 persistent volume objects for each of the volumes. Now, as an end user, I need some storage for the application, and I don't care from where the storage is coming. I will just say that I need 1 GB of storage. So I claim for a storage, and that is known as a persistent volume claim. So this claim then is sent to the Kubernetes, and what the Kubernetes will do is, it will see whether there is any persistent volume which satisfies this claim. If yes, then the Kubernetes will bound this persistent volume to that claim, and then the user can use that claim inside the application. Right? Now, this is something called as a static provisioning in the container orchestrator, because here IT administrator is pre-provisioning the volumes. But in the real DevOps kind of environment, we don't need any manual intervention. And that's where the dynamic provisioning comes into picture. So what happens in dynamic provisioner is that IT admin is not required. The user just raises a claim for a storage. The orchestrator checks if there is any persistent volume which can satisfy the claim. If not, then it sends the request to some dynamic provisioner. And the dynamic provisioner will create the volume on the fly, and it will bind that volume to the claim. So that is what the dynamic provisioning means. So let's try to understand that with the OpenAFS. So there is a developer. He asks for 1 GB of OpenAFS storage. He creates a claim for that. Then this claim goes to the provisioner. The provisioner will finally do a create volume. Will actually create a volume dynamically, which might be some volume of the OpenAFS file system on the OpenAFS storage. And then this volume gets bound to the claim. Now the user wants to use the claim in his application. So in Kubernetes, there is a term called as pod. the pod is just a collection of containers. So you want certain set of containers to be which are dependent on each other to be deployed as a single instance on some node. So that is what the pod means. So what happens is that if you want to use it in the pod, you mount the claim inside the pod. When I say mount the claim, actually the volume will get mounted inside the pod. And once you are done with it, once you delete your application, the volume gets unmounted, the pods get deleted, then the user deletes the claim, it again goes to the provisioner, and finally provisioner will delete the volume. Now here I want to spend some time on the volume lifecycle in the container orchestrator. So, typically when we want to use a volume, the first thing what we want to do is create a volume. Right? Now, and once the volume is created, it could be, so now there is one container which wants to use that volume. And that container would be scheduled to run on some node. Right? So what is the next step? You have to attach that volume on that node where the container will run. That is done by something called as controller publish volume. So it attaches the volume on the node. Right? So your volume is attached on the node, and now your container is starting. Now what the container wants? It wants to mount that volume inside the container, right? Using a bind node. And that is done by the node publish volume. And then your application uses the volume, and when your application deletes, then it calls the unmount. Right? So when the unmount happens, there is an interface called node unpublished volume, which unmounts the volume from the pod. Then what is the next step? Your pod is deleted. Now you want to detach a volume from a node because you are done using it. So that detaching operation is known as controller unpublished volume. And now if you are done using that volume, then you can delete a volume using the delete volume. So this is a typical volume lifecycle. And this is the top one is for the dynamic provisioning because the volume is getting created and deleted on fly. The below one is the pre-provision volume, the static provisioning. So you are pre-provisioning a volume and all other steps still remain the same. Now we will use this. So let me talk about that here itself. So the creation of a volume. So let's say you have a cluster, right, and there are hundreds of nodes. Right? Now, if you want to create a volume, there can be only one instance which can create a volume on the OpenAFS file system or any other storage package. So the provisioner should run as a single, means we can just run a single provisioner in the entire cluster. Similarly, when you are attaching a volume, that can also be a single container which can attach a volume onto a node, right? It can just say that there is a volume 1, attach it on node X, and that request will go to the storage backend, and the storage backend will attach a volume. But the mount and unmount should happen on every node, right? So I will refer this in the CSM plugin where I will explain the various components. So this is a simple diagram. So in the previous diagram we saw there was a provisioner, then there was a mounter, then unmount happened, right? All these things are provided by some storage plugin, and this sits outside the container orchestrator. So container orchestrator sends those requests to the plugin, and then plugin maintains the complete volume lifecycle. What's the problem? The problem is that we have different container orchestrators. And for different container orchestrator, previously we had to write a different volume plugins. So there is a one storage vendor who is writing a plugin for Kubernetes as well, Mesos, Docker Swarm. And the reason is the way the platform is designed. Right? It was not common. So in Kubernetes we used Kubernetes Flex volume plugin. In Mesos there is something called Mesos volume plugin. In Docker there is something called Docker volume plugin. And that's where all the orchestrator people came together and they thought that why not write a single specification? And if you write your plugin based on that specification, it will work seamless across all the orchestrator. And that is where the container storage interface comes. So previously, without container, so CSI stands for Container Storage Interface. Before CSI, this is how the things used to look. So kubelet is one of the components on the worker node which is responsible for mount and unmount operation. So typically, it used to contact the volume plugin, and the volume plugin used to talk to the external storage. Now this is the container storage interface. I'll explain this figure, and when we will see a demo, I will relate that whatever components I'm showing you. So there are three components we are seeing here. One is the external component. This is what the storage plugin will write. Right? The storage vendor will write. These are the components present in the storage plugin. Then the middle one is the external component, and it contains helper containers, which helps you in provisioning the volume, attaching the volume. What does it mean? It means that there is some help provided by the container orchestrator for you. So now your plugins becomes thin. You need not to take care of lots of things because the Kubernetes has provided those helper functions for you, right? And then there is an orchestrator. So let me start with the plugin. The first component in the plugin is the identity server. So as the name says, it tells you what's the identity of your plugin is. Like, what is your plugin name? What is your plugin version? What are capabilities your plugin is having? Whether it is having capability of provisioning a volume, mounting a volume or not. And it is also having an interface for probing your plugin, whether your plugin is active and it has not gone bad. Then there is a controller plugin, a controller server. And what is the responsibility of controller server is that it takes care of provisioning a volume, right? Like create volume and delete volume, and also takes care of attaching and detaching a volume on a node, right? And then there is a node plugin or node server, which is responsible for mounting and unmounting a volume. So as I explained in the volume lifecycle, the controller server, which is responsible for provisioning and attaching, has to run only there should be only single controller server in the entire cluster which can take care of it, right? But then there is a node plugin which takes care of mount and unmount. It should run on all the nodes in the cluster. Now, these are the helper containers like external provisioner and external attacher. So whenever the provisioning request comes from the orchestrator, it first goes to these helper containers, and then these containers do some kind of work, and then just route the create volume call to your plugin. So in your plugin, you just need to create the volume, and all other orchestrator related stuff is taken care of in that helper container. And similarly in the attacher. There is one component as driver registrar. So I told you that on all the worker nodes, there is one component running as kubelet. And what is the duty of kubelet is that whenever it gets mount request, it sends that mount request to the plugin, right? So kubelet has to send the mount request to your node plugin, right? And what happens is that there is a driver registrar container which registers your plugin with a kubelet. So you can say that with the driver registrar container, the kubelet becomes aware that okay, there is an AFS plugin running, and if some mount request comes for it, I have to send it through. Now these are the different. These are the different components, right? These are the different containers which are running on the host node. How do they talk to each other? Right? So normally they talk with using a Unix domain sockets, right? So the plugin creates some Unix domain socket on the host node wherever it is running, and that is how the helper functions talks with those with the plugin using Unix domain socket. Right? Yeah. So now with this, let's try to understand. So there is a provisioner which is running. There is a single provisioner which is running in the cluster. So right now my cluster is having master and 3 worker nodes. So there is one single provisioner running, and this provisioner is OpenAFS helper provisioner. the external provision, right? So it is watching the master for any provisioning, volume provisioning request. Now there is a user, and the user asks for 1 GB of OpenAFS space. So what he will do, he will run a kubectl command here, that it will send the desired state to the master. Then this request will go to the provisioner. Then provisioner will query the plugin running here. That okay, this is the provisioning request for OpenAFS. Is this plugin for AFS or not? Right? And if it is, it sends that request to the AFS plugin. The AFS plugin will call a create volume, and it actually creates the OpenAFS volume on the storage file. Right? Now there is a kubelet, and kubelet is watching for any mount request, right? For the pod or the application. So user creates an application. So kubelet sends the mount request to the plugin, and plugin mounts the volume inside the pod. Right. Now user deletes an app. The plugin, the kubelet calls unmount to the AFS plugin, and finally that plugin is unmounted. And if you delete the volume gets deleted. So let's have a look at the demo of this. So any questions till the demo is up?
So you have this. So there's this plugin that handles creating volumes for the dynamic provisioner.
Yeah.
So do you what handles? Some sites may have certain policies, like which file servers they want it to go on, that kind of thing. Is this this handles all of that, or do you call into some other thing a site might have for provisioning volumes?
So currently, for this POC, it doesn't have that much intelligence. So typically, what we provide is in the storage class, the admin explicitly provide that this is the file server you have to go, this is the partition you have to use, and when we create a claim, we use that storage class. Maybe in the demo, that thing will become more explicit.
Okay.
Okay. Okay, so I am having a 5 nodes Kubernetes cluster. One of them is a master node, and the other 4 are the worker nodes. On all the nodes, AFS client is running, and we have taken the tokens. So right now, this is required for this POC. Now, in the AFS space, we are having one global path which is configurable, where we will create a symlinks of a Kubernetes volume to the OpenAFS mount points. You will see it in the demo. And there is one global file which is a kind of a map. So Kubernetes understands volume as a volume ID. So this map maps that volume ID to the AFS volume structure, like AFS mount point, volume name, etc. So let's have a look at the plugin YAML file, right? So I told that the node plugin has to run on all the nodes, so it always runs as a daemon set. So in Kubernetes, there is something called a daemon set attribute object, which makes sure that the plugin runs on all the nodes. Then there is a driver registrar. So there was one helper container driver registrar. So this driver registrar registers your plugin with the kubelet, and this happens using the Unix domain socket, that is CSS on. And on the host part, that is a path for the CSS on. The plugin uses this Unix domain socket to talk with all the other components in the cluster. And this is the node name, which is the host name where the plugin is running. So let's look at this path which is mounted inside the container, where the Unix domain socket is there. So if you see this, if you see this, we have bind mounted the host path, the path on the host inside the container as /CSI where the Unix domain socket is. We also bind mount the symlink path, the configurable path inside the plugin container because we need to create the symlinks. Because container doesn't have access to /AFS. So we have to byte mount it inside the container. Now, that's what it shows, that it is inside the container, this symlink path is byte mounted at the /AFS location. Now let's look at the provisioner YAML file. This is the helper provisioner provided by the Kubernetes. It is running as a stateful set with replica 1 because we need only one controller and one attachment. Right? So it runs as a single instance, and because the provisioner has to send the request to the plugin, it should run on the node where plugin is there. So we use something as a pod affinity attribute to make sure our provisioner gets scheduled on the node where plugin is there. And you can see the name of a provisioner is CSI provisioner, and it uses this Unix domain socket, which the plugin has created. And using this Unix domain socket, it talks to the plugin. Now, there are other files also like attacher and snapshotter. So right now, I'm not using attacher because I'm assuming that on all the nodes, the AFS is already mounted. But I think in attacher, we can put a code where we can actually mount the AFS if it is not mounted on that node. So that's still missing out. So let's now install this plugin. So what we will do is kubectl create, and let's install it. So it is creating all these objects. Let's watch on the pods, the containers which it will start. So here you are seeing now the attacher is started, it is no operation right now. The provisioner is now running, and since I am having 4 nodes, the worker nodes, there are 4 plugins which are running on 4 different nodes. Right? So now they will come into the running state. So now all the pods are running. So our CSI driver is installed, or CSI plugin is installed. Now there is something called as a storage class in Kubernetes, right? And if you describe the storage class, so let me pause it here. So the question you asked, right? Where on which file server you create a volume and all. So this storage class is something created by the Kubernetes administrator, and when you raise a claim, right, you will use this storage class, and all these parameters will be passed to the plugin, and then in plugin you can fetch these parameters and create the volume. Right? So for example, the cell name, host name, partition, the pathway you want to mount, and there is something called as SSH host here. So there is something called SSH host here. So when we create a volume, we do a was create kind of command. Now these utilities are not present in the container, right? So currently we use a SSH connector. So what we do is we SSH from container to the host and execute the command. So that is how the volume gets provisioned. Right.
Is it
And
yeah. So in that host we use local auth then to.
Sorry?
We use local auth
Between the
on the SSH host. Does it have
so
the host keys?
Yeah, we use
Could you repeat the question, please?
please?
Do we use local auth?
No. So because I have already taken the tokens on the node, on the node where the plugin will run, so you don't need to.
Oh, okay.
So you can see the provisioner name is CSI OpenAFS, and when we will create a claim, and there you will see that we will use this storage class. So when the persistent volume claim will be sent to the orchestrator, it will see that this is the storage class, and based on the storage class, these parameters will get passed to the provisioner and then to the plugin. So let's have a look at the PVC YAML file. So that's what I said, that we're creating a claim. Name of the claim is CSI PVC1. We want 1 gig of storage, and the storage class we want to use is CSI OpenAFS SC, which I just showed you. So now let's create this persistent volume claim. So PVC is created now. Let's get that PVC whether it is created. Yeah. So the PVC is created and it is bound to some volume with the name PVC with some random number. And we will see that this is the symlink which will get created in our symlink global path, which will refer to the AFS mount point. So this is the symlink which gets created in the AFS space with the same name of that of the PVC, and it is actually a symlink to some volume. So AFS is having the limit on the volume name, I think 22 characters. So we create a hash based on some parameters, and that's how we come to that number, the hash value. And this we store it in the global map so that we can fetch the volume details. So now what we will do is we will use the claim CSI PVC1 in some application. So there is a CSI app. So we are creating a pod here, and what we are saying is that there is a claim name with the name CSI PVC1. Have it as a volume name as my CSI volume, and then inside the container mount this volume on /data. So inside the container it will be mounted on /data. So let's start the application of pod. So what will happen when we are starting this pod? The attach will happen, and then the mount will happen, right? And the request will go to the kubelet. Kubelet will send the mount request to the plugin, and plugin will finally mount the volume inside the container. So currently container is getting created and it is on some node DG node 5. So now container is running. Now we will go inside the container and we will write something on the persistent storage on the OpenAFS. So we are going inside the container now. So the name of the container is my CSI app1. We are starting a shell here. So now we are inside the container. And if you do a mount of AFS, you can see AFS is mounted on /data. Now this is the bind mount, simple bind mount in a different namespace. Now let's write something into this. So we are writing some hello message from container. So this is the name of the file. So in /data, we are writing something to hello message file. Now let's come out of the container. Now we are on the host. Let's see whether this file gets created on our OpenAFS. So this was the path for this particular persistent volume claim. So let's go inside this mount point. So this is the file which is actually came on our storage, OpenAFS. And this is what we have wrote. So this is how we have made OpenAFS as a storage inside the container, right? On the OpenAFS side, we will just look how it looks. So we will just run some fs examine command here on that path where the volume was created. So this is the mount path. So /fs. So this is actually the volume which got created by our provisioner, right, on the storage packet. Now what we will do is we will delete the application. So when we delete the application, what will happen? The request will go to kubelet. The kubelet will unmount will send the unmount request to the plugin, and that's where the unmount will happen. And later we can delete the claim also. So the application is getting deleted. Takes a little time. So previously in Kubernetes it was very much I think asynchronous, right? It doesn't use to wait. You run a kubectl delete and it comes out. But now in the latest version it makes sure that
what I usually do is I do the kubectl delete in the background and watch the state of the objects.
So now the application is deleted. So now we are deleting a PVC. So what will happen once we delete a PVC? Since it was dynamically provisioned, it will delete the volume on the storage packet. So if we look at those paths now, all those paths will get removed. So now this path is not there, and somewhere we will see that the symlink which was created, even that symlink will also not be present. So we just go a little up here to get that path. This one. Yeah. So this is the symlink which we had created. So now it is also gone. So here we have seen the complete volume lifecycle. We created a volume, we used it in our pod, we deleted the volume, and we deleted the claim. So one thing you might be thinking that I am creating these symlinks, right? Why this special way of going through, right? So in CSI plugin, there is one interface called as list volumes, right? Where you want to list all the volumes which has been created. And one way is that you can attach some attribute to your volume and just do was examine and get that volume list. But I found that is very much time consuming. So I put everything in the symlink, and when that list volume happens, just to ls and get all this stuff, all the volumes directly. So that is one thing. Another thing, in the starting I showed there is a map between the volume ID and the volume structure. So I want to get rid of this map. So what does this map contain? It contains the mapping between the Kubernetes volume ID and the OpenAFS volume details, right? And the reason is all the interfaces in CSI just get this volume ID, and it is only the plugin writer who has to make sense of this volume ID and get the volume details. So one way is to get rid of that global map is to put the information in the volume ID itself. Right? Make a volume ID such that it contains all the information. The only problem I am facing is the CSS spec says that the volume ID should be one. It is a string, right? But spec says it should be 128 characters. So that mount path can be anything, right? And that's where I think when I create this configurable path, right, that symlink path, maybe that might help if we put some restriction to the user. The actual global path can be dismissed. Yeah, so this is it. Any questions?
You may have said this and I missed it. How are the so you have access to that volume inside the container, but obviously you need tokens, you need rights to do that. So how is the access managed to that? Like, is it running with a key tab that's obtaining tokens, or it's used the caller's tokens?
So in this POC, we take the tokens on the node. On all the worker nodes, token has to be there.
Okay, so it's like, yeah, it's a global.
So so I think that is one missing piece. How to handle the security angle here. So yeah, we have to granularize that.
Well, how are you doing it? Is it running like with a key tab that refreshes its credentials over time, or it's just somebody's credentials? Like
So typically we take some DGP and then the kind of AT log to have that tokens in the session.
But yeah, so it's just running like in the background, refreshing them.
Right. So yeah. So maybe right now in the POC that infrastructure is not there, that it can run in the background, but maybe some different approach can be used here.
Okay.
Still thinking on that.
If I may?
Yeah, please.
A container is acting like a little mini EM. So one way to do it is just do it the same way you do it with a standalone app, which is embed inside your container ways to refresh the keys the way you know. That's flawed, but that works. What you really want to do is associate an identity with the container, but not have the container have the responsibility of authenticating and refreshing.
Yeah.
And the movement in the container, in the Kubernetes and container world, I mean, there's fundamental problems with Docker, but putting those aside, the architectural trend, because I've been involved in the Kubernetes community, is to have a sidecar object container in the infrastructure that's responsible for establishing and renewing keys. That's controlled by the administrator, not by the application doesn't bundle anything into their container. Doesn't even have to have AKLWK in it. It's doing that as a proxy, and then associating it with the process
yeah,
tree.
like another service that requests, like it's requesting access to it, so in that thing. That's
Right, but it's blind. It's blind to the container.
Yeah.
You know, it's specified in an administrator object because there's kind of this logical separation of what users specify, which is what my application needs, and secrets and things like that.
Yeah, but I still wonder in those cases, like you could have identities dynamically created, like per container or something like that, or you could have them pre-provisioned or whatever. Because nobody needs rights to that volume besides that one container.
Yep.
If you don't use that, so you could create the identity on that.
Yeah, this design pattern called an operator in the container orchestration world, where you basically have a program that does that for you, that's you write, or the storage provider writes, that does all of this for you, and it's just sort of watching the system for you.
Sorry, go ahead.
Yeah, and one thing is that yesterday you gave the talk on the native commands.
Yeah.
Right, so right now we are using FS and KM commands, right? But the CSF plugin gives the helper functions for now. But once that is checked, then we can directly use it.
Yeah, then that would.
There's other stuff that had been in discussion. For those of you who care, there's a storage sig for Kubernetes that meets every other week, and I've been involved in that for a couple of years now. Finally, in 1.14, which is the current iteration, they have topology aware scheduling. Because it used to be the scheduler didn't really know about storage, which was a problem. So you can now do things more exotically, like a lot of the container orchestrators are now spanning multiple clusters. So you might have one Kubernetes cluster with some nodes in house, some nodes in Azure, some nodes in AWS. You might have in your cluster some machines that have a file server locally and the cache is in the same rack. So you can do things like, I want to mount this volume, I want to be mounted on a machine which has a file server near it. So that would be something you specify in your storage class. The Kubernetes plugin, the one that I wrote, is aware of that, watches that, it knows the topology, and so it communicates back during the CI/CD process. That's my preferential schedule. And you can even do things like migrate file names before you schedule, if you wanted to. So there's a lot more functionality that. So it's just our code.
Yeah. So
Simple matter of coding.
the
Just a simple matter of coding.
No, but before 14 you couldn't do it.
yeah.
I'm sorry.
Yeah. So you've written this. This is like there's some limitations here. Obviously, this is like a work in progress. I assume. Are there plans for this to be like public? I'm assuming there's a Kubernetes like marketplace or whatever you call it for plugins and stuff like that.
So that's what I was thinking, that currently, as I told, that there is some fine tuning. I don't need a deep like map file. I don't need any database in my plugin. I need to make those changes, and maybe then I can put it in the community, and maybe community can review it, and maybe it can be placed somewhere in some source tree.
Yeah. So I mean that's not something that would be in OpenAFS. I would assume that's like it's a Kubernetes plugin, so it belongs in the Kubernetes world.
Yeah. Okay. Any other question? Okay, thank you.
Thank you very much.